So you're all welcome to today's workshop. I would really like today's class to be very interactive because it's design and sometimes you can get stuck somewhere. So for you to be able to call my attention where you don't understand. So for today, we would have a look at computer-aided design, Fusion 360 overview. We'll look at 2D drafting, 3D modeling, and then have some hands-on practice for today. And then, before I talk about the objectives, I would love to ask if anyone has explored designing a robot or anything, or used the design software before.
I've done SolidWorks and Tinkercad. How close is that to Fusion 360?
Okay, Tinkercad is more like, they are kind of related. It's more like for beginners, so it's still design, but for like starters. Okay, that's great still. So for today, we'll be able to understand the mechanical design process for robotics. Like I said initially, would explore 2D drafting and 3D modeling concepts, and then understand the design for manufacturing principles. And at the end of the entire workshop by tomorrow, we'll be able to design a 4-wheel drive robot chassis. Okay. So what is mechanical design? Mechanical design is more like a structured process of turning an idea into a workable, manufacturable product, whereby you're able to apply some principles, use shapes, bring them into structures for able to bring a product to life. And in robotics, every joint, every wheel, arm, or chassis starts from mechanical design before you talk about electronics integration or even programming, before all of them can be applied. Mechanical design is basically about turning those ideas you have into real working systems. Take, for example, you want to build an autonomous robot car that does a navigation in a farm. That's the value you're putting out there. So that whole concept is an idea. For you to bring it into real life, you need to apply some design concepts. You need to know what and what components to bring into Fusion to put them together for that value you want to create to come to life. And in robotics, every design has to balance functionality, strength, cost, and manufacturability. In essence, robotics design forms the foundations for robot hardware development. So why mechanical design? In robotics, mechanical design is more like the backbone, and it determines how stable, functional, and manufacturable a robot will be. Manufacturable in the sense that when you design the robot, it's able to like undergo standard manufacturing process. It's able to be produced, and it's going, after being produced, it's going to give you value for producing it. That's what I mean by manufacturable. And then in this design, it's not just about creating shapes or even structures or forms, but ensuring that the design works hand in hand with the electronics and the software that you'll be integrating it with. So in essence, mechanical design ensures collaboration with both the electronics, control systems, and then the software programming aspects. So I'll be walking us through the mechanical design process. Not just about mechanical design, but every system has a process which it works, and it's always nice to follow those processes for you to achieve the desirable results that you want or that you aim to have. So for mechanical design, it comes with about 7 to 8 processes, whereby you have the problem definition. For the problem definition, you need to understand that for you to build a robot, it should definitely solve a problem. So you have to define the problem that you're solving, the objectives of that your solution, why exactly you're building the robot, and why exactly you should go into designing that robot. Then we talk about research and requirements. You need to gather a lot of information about what you want to build and design. You need to understand the user needs, the market survey of that product, if the users is going to like appreciate what you're building. You need to understand certain constraints and specifications. Constraints in the sense that, okay, let me say you're building drones. There are some places that do not accept drone navigation around certain areas in some countries. So you need to understand constraints behind the products you're designing, behind the robots you're designing. You need to understand some of the regulatory laws and all of that, and then specifications based on user needs or company needs. We now talk about conceptual design. For conceptual design, at this stage, you need to then start brainstorming. You're done with your research at this point. You now start brainstorming about the robots, get multiple ideas, roll out ones that will not give you the value that you want, and then select the most promising idea. Then when it comes to preliminary design stage, this is where you now have your rough sketch, your layout, you get your robots coming in place in tiny bits, whereby you will then have some little CAD models drafted out in your paper. Then we move to analysis and simulation. At this stage, you're done with your first modeling on your software, be it Fusion 360 or SolidWorks or just any design software that suits that robot you want to develop or that product you want to develop. Then when you then have to analyze it, you check for strength. Can this robot give this value? Can it be able to carry this weight? Is the material used in producing a robot fit enough for the value you're offering? You need to analyze it using softwares for analysis. Some softwares like ANSYS or Abacus, there are analysis softwares out there. Even Fusion has a part of analysis where it runs. So it depends on what value you're creating with the robot. I'm using the robot for this case study. Then we talk about the detailed design stage. At this point, you're done with your analysis. We've gotten kind of user feedback from the first initial testing stage. You've actually gotten a little approval where to make amends. You've gotten places where errors can be developed. Then you then create a final CAD model at this point with proper dimensions, tolerances, and proper material selection, because the material you have to use for a robot is very important in the sense that it has to withstand enough strength, and then it has to withstand stress too, in case of buckling or maybe any load that is being suppressed on it. There should be a level of stress in material you're using to develop your product or you're using to build your robots should have. Then we talk about the design for manufacturing stage. This is where you can now start mass producing for the first MVP. This is just like where you have your minimum viable product level, where you also send out for another user feedback and then looking for more things to improve. So at this stage, you ensure that your design is efficient and it can be economically produced. At this stage, you know that, okay, your design has passed certain number of stages and it fits in within the costs and the revenue too. It balances it all up on the gain, revenue, and then the value it's going to give. Then we talk about prototyping and testing. At this point, you started building your prototypes for the final stage. You do a series of testing, get a final user feedback, and then we approach the final stage, whereby you now have to deliver your design package with detailed drawings, detailed assembly diagrams, bill of materials, and then instruction for manufacturing for mass production proper. So this design process is actually iterative in the sense that you may need to cycle back to earlier steps when issues arises. Take, for example, you've approached the preliminary design stage and you notice that, okay, this robot is not supposed to be a two-wheel drive robot. It's supposed to be four-wheel drive. You have to go back, do your research on why, check out the weight of what is going to carry, and determine, okay, what control systems are we going to use? What microcontrollers are we going to integrate? What are we going to do in this worst case scenario? Or if anything worse happens. So sometimes it's not linear. You need to iterate and ensure that whatever you're building brings the value that it's supposed to bring. So these are like pictures of design products. This is a model of a four-wheel drive robot, which we'll be designing at the end of the class by tomorrow. Then this is a combination wrench designed with Fusion 360. So we talk about computer-aided design. So normally people talk about CAD, and then some are like, what is CAD? I mean, people always say CAD is similar to mechanical design, which is kind of, I would say it's similar, but not really, because there are a lot of CAD softwares that are not for mechanical design. So basically, CAD is computer-aided design. It's the use of computers for your design process using the software that is required for that process. Why I'm emphasizing that it's similar but not similar is because there are other CAD softwares that are not for mechanical design. Something like Revit. Revit is for civil engineering design, for structures and all the concrete slabs and all of that civil engineers do design. So for this mechanical design today, would actually know that for mechanical design, CAD is at the heart of mechanical design, in the sense that most mechanical design systems cannot be set up or done without using computer-aided design. So the CAD software allows us to design parts with precision, to test them virtually, eliminate errors, and then easily update the designs when needed. And then it makes things fun and better. And I would actually like to say it makes things smooth sometimes. So why learning CAD, or why CAD in the first place? We need to ensure accuracy and precision. We need to ensure that your modifications to design are made as at when due, because one thing is to use your hands to create 3D modeling, and then when there's actually a mistake or an error encountered, you then have to erase the pencil diagrams you made, or the hand, well, let's say the hand-drawn 3D models you made, for it to effect the mistake. So CAD makes it easy to modify designs. Also, it's easy for you to visualize your product before manufacturing when you use CAD for your design. And then it's also easy for you to collaborate and document your design. So there are different CAD softwares for mechanical design. We have Autodesk Inventor, we have Fusion 360, we have AutoCAD, SolidWorks, CATIA, Creo, Onshape. There are a bunch of them, but then I would like to add that some of these softwares have similar uses, but they have different industrial applications, in the sense that there are specific industries that use each of them. Take, for example, automotive industries use SolidWorks and CATIA to a very high extent, but then product development industries and then some robotics industries too, I've seen a lot of robotic startups that will require you to know Fusion 360 because of its easy navigation process and then parametric design permission and all of that. We'll get to that. So just to add that, the CAD software you're using to design, depends on what you want to achieve. or what you want to develop to give the value that you want. Okay, so we'll be using Fusion 360 for this class, and then I know you would love to know why we are using Fusion. So, like I was saying, I know we would all love to know why we are using Fusion 360. So, first of all, Fusion 360 is more like an all-in-one platform where you can not just sketch and model, you can do a whole lot of things. You can run simulations, you can render realistic images, use it for design of other things aside mechanical stuff or product development. Because I know Fusion is used in jewelry industry too for designing your diamond rings, necklaces, and all of that. So also Fusion permits parametric modeling, whereby your dimensions and design constraints can be changed later on, and your designs are being updated automatically. One thing I love about Fusion is the cloud-based integrations and team collaborations, in the sense that a couple of people can work on the same design and they'll see it live being modified while work is being going on. And then it's cloud-based in the sense that your designs are saved virtually and also when you're offline. So Fusion actually ensures that your designs can be iterated. There can be future advances when it comes to implementing user feedback. That's also where parametric design and direct modeling falls in. And then one beautiful thing is that it's free for students and startups. Fusion always gives students free license for up to a year, and they can renew it annually until they are done with school. So we quickly talk about 2D drafting. This is more like a step you have to take before you do any modeling. It's more like all of the little sketches you have to do before you achieve a drawing. Take, for example, let's say you want to draw a cube. Before you draw that cube, you definitely have to assemble a whole lot of lines and corners and everything for the cube to be drawn. So that's just the basic, or let's say the idea behind 2D drafting. It's more like representing your ideas, your models in 3D views, first of all, before you begin to bring them to life in 3D format. And 2D drafting usually forms the basis of communicating, especially in design engineering. So first off, you need to understand views in these technical drawings. I don't know if any of us have a little background in design and drafting, but I would actually have to talk about that. When you want to draft or do a design on, let me see, an object, I'll use a stock cube for an example. You need to actually look at that stock cube and know, okay, what are the views? How am I seeing this stock view for me to draw from? Let's say your drawing is as a real life drawing. Your drawing, as you see, you're actually having views of that stock cube. We have the front view of the stock cube. We have the top, the right side, the back, and the bottom. So this is the same way it's applied in designing some concepts, right? So when you're designing, you need to understand the different views and then know where to start your designs from. And this, most times in mechanical drawings, 3D objects are represented using 2D views. So more like most times, the front view is a primary reference because definitely you're going to be drawing from what you see. You're going to be, even if it's from your imagination, from the place you're starting to see is where you start your design from. I don't know, when I was in school, they would say you need to have a third eye, in the sense that when you're drafting something, even if it's in 2D, you need to have a kind of creative thinking to be able to arrive at the 3D model and know how beautifully it can come up. So it's important to know that the front view is usually the primary reference, although most people prefer the top and the right views. When we get into the software, I think you would understand this better. So another thing also is the orthographic and isometric views. Now in design, we have these two types of views, this orthographic projection and isometric views. And then orthographic projection is more like a symbolic way whereby a 3D model is split into three views: the top, the side view, and then the plan, which is the front view, right? So it's more like you have three views of an object, and then if you put those three views together, you're able to like assemble them back into a 3D model. So an isometric view is more like a 3D drawing already, usually in 30 degrees angle to help you to visualize your design. It's more like, I'll see a stock cube for an example. You place a stock cube on a table and it's positioned at an angle. You're going to see at least 90% of the stock cube, and you're going to be able to represent that on paper. So for the sketching basics, we need to understand that every CAD model starts with a 2D sketch, and then the basic entities of a sketch are usually lines, circles, arcs, rectangles, polygons. We all know what polygons are. And then these form the building blocks of all the complex parts that form a design. Talking about the constraints and dimensions, the geometric constraints are more like some kind of specifications that control the relationship between the lines you've drawn, the circles, whether they are going to be concentric, that is parallel to each other, or your lines are going to be parallel, whether your lines are going to be at angle 90 degrees or at whatever angle. While the dimensional constraint gives exact sizes. Take, for example, let me say you are, for the robot chassis we designed today, when we see that, okay, the length of the base of the chassis is giving us, let me say 150 millimeters, then your dimensional constraints will actually give that this is exactly 150. So dimensional constraints are for you to denote the exact sizes that you want your design parts to be. So normally a good sketch is usually fully constrained, meaning that all the geometry is usually designed for clarity, because definitely in engineering design, it's not just one person that does the design. Design is always done in collaboration because we need to ensure efficiency and ensure that that value is being given. So to ensure that your drafting is done excellently well, you need to ensure that your sketches are kept simple and uncluttered. Like, your complex shapes can be broken into multiple sketches just for clarity, to reduce ambiguity and all of that, to ensure that every engineer in question, because definitely not everyone can interpret designs, but ensure that another engineer picking that up can actually be able to interpret that, okay, this is what you're trying to achieve, right? And then you need to always fully constrain your sketches in 2D before extruding in 3D. How do I mean? You need to ensure the dimensions, the measurements. Dimensions are basically measurements. The dimensions of each part, each line, each angle is given and fully outlined. And then always use consistent units. If you're using millimeters, stick to millimeters, try your design. If you're using inches, stick to inches. Just ensure you apply proper scales for more clarity in your design. So this is more like a 2D draft, and then we can see it. This is the 3D combined view from this 2D you are seeing here. So this is more like the top. I was talking about three views: the top, the side, and then the front view. So the top view is this one. I don't know. Can you guys see my arrow? Please, can you see the cursor?
Yeah.
Okay. So this is the top view of this 3D model. This is the side view. You're looking at it from the side, while this is the front, right? So this is another one too. So this is why views are really, really important when you're sketching or designing an object, especially for at the 2D drafting stage. Okay. So this is more like a 2D drafting of a wrench. The wrench okay, this is another one. The one I showed initially was a combination wrench. So this is more like how an object should be properly constrained, all the dimensions outlined to ensure that when an engineer is going to pick this up to do a 3D model, he's not confused. He goes straight into production and furtherly modifying the design without having any issues. So we're going to talk about 3D modeling basics. So when moving from 2D drafting to 3D modeling, the first step is to understand how to navigate the workspace. And in CAD, like I said initially, we work with the isometric and perspective views. Let me go back. Oh no. So now this is not in isometric view. It's similar to isometric view. It's in an oblique view because it's more like, it's looking like this is an angle 45. So literally an isometric view, the 3D model should be positioned in angle 30 degrees, right? So like I talked about when I started talking about the 3D modeling, we need to understand how to navigate the workspace. You need to understand the views, right? So now when you've seen that, okay, this is what you want to design, you've seen that this is your front view, your top view, your side view, and your front view. You then know, okay, this is where I'm going to start my design from. If you're comfortable with starting from your top view, that's beautiful. From the side view, still beautiful. So I'll go back to where I was. Okay. So the basic features of a 3D modeling space, I'll be like, okay, using Fusion 360, we have extrude, we have revolve, we have sweep and loft. So while we'll be navigating the space, we'll actually look at these tools. They are quite easy, right? Then talking about sketches, all 3D models always begin with sketches, like I said. And then a sketch is usually turned into 3D using the basic features I just mentioned initially, the extrude, revolve, sweep, and loft. And then your constraint and dimension actually keeps the sketch controlled, because if your line is 10 meters and then it forms a rectangle that is, let me say, 10 by 2 meters or 10 by 2 inches, whatever metric system you're using, you should then know that those defined measurements you've given to it is going to ensure that when you're converting to 3D model, it still follows that measurement you've given it before. So talking about assemblies, assembly is more like putting multiple parts together, more like your wheels, your chassis and mounts. So this joint defines how parts move relative to another. When you're designing, there are different parts that come in place. So it's always important that during your 3D modeling, you're able to join everything together. So visualizing and rendering, basically, when you are done with your design, you then look at the material. That is because you're using a software, obviously. So you have to ensure that you apply the proper materials, use exploded views for more complex 3D models. And then you need to always remember to start simple, build it step by step, use parametric design so that you can update your changes automatically. So this is a 3D model of a wrench. I share the 2D drafting done before the wrench was converted to a 3D model. So we're having a breakout session now so that we can have an overview of the Fusion 360 interface and do a little bit of 2D drafting and then create these 2D models before we go over to designing the robot car.
So do you want to have breakout rooms, Chidinma?
I think since there are few, we can just do it together.
Yeah, I think that's a good idea because there's only 8 people here and some people didn't get the pre-work done. So if you want to just walk everybody through it together, and I put the pre-work in the chat for those of you who want to try to get the software downloaded, but it may be best for you to just do it right here with everybody.
All right. Okay. Please, I would like to know if, like, I'd like to know those that have done that did the pre-work session, that maybe they downloaded the software initially or something. Let me check.
Oh, okay. We do have one person who said they did the pre-work, Ajisafe Mosimulolua. But I'm not sure if there's anyone else. If anybody else did the pre-work, please put it in the chat, which is basically, it looks like downloading the software was the main thing.
Yeah.
So if you have the link to the software, you can actually go ahead and download it now. It looks like you get a free trial with a student email address. So Chidinma, you go ahead and just show us how you would make it. And if they have their software, they can watch the video later. So if you could share your screen, share the Fusion 360, and show us how you made your models, that would be helpful.
All right. Okay. I'd already started using this software before now. So, okay, so for a starter or someone that has not used this software before, it's recommended that when you're done signing in, you can decide to create a new project. You go to home, click on new project. If you click on new project, you basically create a new project. I don't know, my network is being slow. Let me check. So when you're done creating a new project, you then click on your preferences. Please give me 1 minute. I need to check my network because there are some things that are not showing up. Yes, it's working now.
Oh, okay. Yep. Go ahead. I told everybody to work on downloading their software while you were doing that. So you go ahead.
Okay. So this is the Fusion 360 interface, and it's more like where we do the designs, where you create your models. So if you're new to this and you're able to open up to these parts, you definitely see a home page like this. Then you create a new project. You give your project a name. Let's say Robot Car. Then after that, you can now decide to create a new folder for this project. I'm just walking you through because like not everyone has used the software before. So you can decide to now say, you can decide to give this folder 3D models. Now for your design, it's always
hold on one second, Chidinma. Aji Vase is saying, can you start again? So maybe go back to
okay.
the point where you were at create new project, because that might be about the time when everything kind of locked up, and just make sure everybody can get here. So start from home screen,
Okay.
create new project.
Okay. So everyone can hear me now, right?
Yes, we can. So yeah, so just go back to the home screen and walk through what you did.
Okay, this is the home, right? You're seeing a whole lot of things here because I've been using the software. So you can just click on new project here, because in your screen, you'll just be seeing the default project that comes with the software, right? Is everyone with me?
Either come off of mute or type in the chat if you're following. Okay, let us know how you're doing, Ajif Safe and Cynthia and Amanu and everyone else. If you're following, okay, put a thumbs up or a reaction or a +1 or something so she knows to move on. And Wella, Amanu, thumbs up, reaction. Cynthia, how we doing? Cyril, how we doing? Thumbs ups, thumbs up. Okay, we got thumbs ups. Okay, keep going, Chidinma.
So we create a new project, then we give a project a name. This time, let me say BIR Robot Design class. Click on enter and you created a new project. Then you can now click on the project you created, and then you now create your folders for that particular project. Now, this folder could be on, this could now be these 3D models we'll create now. Then another folder could be for the Robot Car Chasis. Did you all get that? Okay. So it's always important to save your design. So now that we already have a window open, the first thing you have to do is to save your design. So we click on this save button. Let me go back again just for clarity. This is the save button on the navigation panel. Then we click save, or you can just use Control S. Then I would name this particular design page model A. And then you need to choose where the location where you'll be saving it to. So I want to save it to 3D models, which is under the BRL design class project. Did we all get that?
Make sure you're giving reactions or putting in the chat so Shajima knows to keep going. Thumbs up, thumbs down.
Okay, so we've saved that. Another thing to do is to go to your preferences, click on your account icon, go to preferences, ensure that your modeling orientation is in the right orientation. I prefer using Y up because I like designing from the top most times. So if yours is set to Z up and you prefer that, that's fine. Depends on you. But for me, I'll be using Y up. Then you check your units. You see the section for default units. I'm using millimeters. If inches is fine for you, still okay, because obviously this is a class. You can still go back later and tweak things up. So I think that is all for the preferences, and we are good to go. So I would go about the overview. So first of all, this whole area by the left, where my cursor is being spiraled around, is the data panel, where all your projects and files are being stored. We've seen how to save your works in your projects and in your folders under the projects. Then this is the toolbar. Let me close the data panel. This entire place is the toolbar where we have the design and other workspaces. Now, other workspaces in the sense that for design, you do your 3D modeling and design and everything. Generative design, whereby you actually do a little bit of performance for maybe mobile robots or any linkages in motion. Let me say chain reactions or links between a robot arm, something like that. Then rendering is when you give your design a realistic look. Animation, where we ensure that we show animation for exploded views of your 3D models. Simulation, I talked about simulation in the mechanical design process, where you analyze the strength of your design, know where there's much stress and where stress can affect the design that you have done. This is manufacturing workspace, whereby you can now begin to tweak your designs and ensure that they are manufacturable for either 3D printing or maybe laser cutting or any manufacturing process you want to apply. Then this is the drawing workspace, where drafters basically use people that do drafting purely. They don't really engage in 3D modeling. They just draft blueprints and send to those that do 3D models. Then electronics workspace, Fusion recently added this for PCB design and integration of electronic components when you're designing. So we're sticking to the design workspace. So still on the toolbar, we have the create section, we have the automate section, modify. These are 3D tools. Also, then for assemble, where we will have to assemble the entire design, when we have different parts design, inspect, construct, we are all seeing that. Then we have the browser. There's usually a browser at the left panel. I don't know. Where am I? Okay, yeah, yeah. When we start a design, as you implement everything on this model, the browser tells you when you add a body, when you add anything, implement a sketch or anything, it tells you exactly what's going on. Then this is the navigation panel. Let me say, okay, the navigation panel takes whatever thing you modeled around. I think I need to use something. Okay, this is one of the models we are going to design. So it's one thing I forgot to say, it's advisable to use a mouse when you're designing for easy navigation. Although if you're using just your laptop, you can make use of the navigation panels. So this helps you to move your design around the orbits, while you can get out of that using the escape key. Then pan helps you to move it in a linear direction, up, down, left, right. Then your zooming can help you to zoom in and out. Then this display settings gives you different views. If you want your design to be wireframe like this, if you want it to be with hidden edges, these dotted lines in between. if you want it to be shaded. So it depends on you. I prefer it this way. So we have viewports and all of that. One another important aspect of this interface is the view cube. I talked about different views. So we have the view cube that looks like the stock cube I use as an illustration. So it gives you different views of your objects or your model. We have the top where you can rotate it about. Sometimes if you want to go back to how it was, you can click on the home page, the home icon near the view cube, and it gives you the exact angle that your model was. We have the right and all of that. So this is more like all about the basic features of the Fusion 360 interface. So back to creating the model. So I think we'll start with the first one. So the first thing you have to do after we set our preferences, you click on create sketch. Now, when you click on create sketch, you're going to be asked to choose a plane for you to create your sketch. Depending on where you would like to design from, do you like to see things properly from the top? If you're designing and you feel like from there you can generate the entire 3D model, then that's fine. I'll prefer the top, and it goes this way. I would have loved to show what we are to design. Okay, so this is exactly what we are designing, this one. So we'll have to use this constraint, this measurements and constraints for this. The link to this picture was sent in the chat earlier when I joined, so you can check it out for a guide while I go back to just designing because of time. Um, um, okay, so we start by creating. We're going to do the 2D. We're going to do the 2D. We're going to do the 2D drafting first of all. So the first thing we could see there is a rectangle. Now, if you drop this here, you can click on escape if you want to return any two. Then these are dimension symbols. I think I need to go through some of these symbols. So this is a line where you can just create a line this way, depending on whatever shape you want to form. I just formed a triangle. Now, when it comes to rectangles, there are 2-point rectangles, 3-point rectangles, center point rectangles, depending on what you want. I love using any one depending on whatever I'm designing. So if it's a center point rectangle, it just points to the center and gives you a rectangle. We talk about circles, 2-point circles, all of them, you would see them on your interface there. All of these form the basis for creating 2D sketches, which helps you in implementing further for your 3D models. So let me undo and go back to what I was doing. So from the top, I'm designing from the top view. Now I'll have to dimension because in design you work with dimensions. So this is 40. I'm using millimeters just in case. And this is 70. Now I'm zooming in with my cursor, sorry, with my mouse. So it depends on you. You can use this to zoom in or just choose what works for you. Then we fillet. Now, this modified tool called fillet is used to give rounded edges to an object, in the sense that when you're designing something, you have to ensure that the edges are not sharp, because you're actually going to think about safety when you're designing, right? So we give a fillet, and then the radius is 10, also on the diagram too. So 10 here too, right? Another thing we have to do is to this is the first stage. We'll then finish our sketch. Click on finish sketch. Then next thing, to extrude. Click on this. Click on extrude. I love keeping it in an isometric view when I'm extruding, so that I'll be able to see exactly what I'm doing. So if we can check the measurements of the picture for the model, we can see that for the first layer, it's 20 millimeters. Then we proceed to making sketch again. Is either you click on create sketch and then select the plane, which is on top of this, or you can just click on it and create sketch, anyone that works for you. Then we use a rectangle because we are trying to form the shapes. So we had something like this. And we also had something like this. Okay. This time around, I'll use a line because I will not want to cause some obstructions. Use a line, escape. So we know that there is no demarcation between these two rectangular shapes if we check the model again. So we have to use the trim tool. We zoom in. I like zooming in when I'm using the trim tool to avoid mistakes. Using the trim tool eliminates this. Then we finish our sketch again. We click on this and extrude. This time, you can just type in the values, 20 millimeters, and it's done. Then we create the circle again on this place. You can use, I'm using a center point circle, so if that works, fine. Now, when designing, it can really get confusing a bit as to where to create your circles, the position of your circle. So I'm dimensioning to ensure that it's in proper dimension. So this diameter is 20. Then to dimension from there, from the model, the picture of the model, we could see that between here and here is 50. So we need to put all these constraints in place to make sure that we are on the right path. So again, we extrude, but this time around, we are not extruding for it to form any body. Because it's a hole, we're using extrude cut, whereby you just push your arrow down. Please, I hope I'm with everyone.
Let's give Chidinma a reaction to let her know how you're doing if you're following okay. Thumbs up, thumbs down, straight face. Make sure you're following. If you're not, make sure she knows to slow down or give you some more help. Amanu says thumbs up. Kaya, how's Kaya doing? Ajasafe. You lost me from the circle center part, Ajasafe said. Kaya, how's Kaya doing?
Okay, let me go back.
Cyril's okay. Cyril's doing okay.
I'm back to the sketching part. Is this where it got lost?
Maybe something about the center of the circle is what Ajisafe said.
Okay, the dimensioning, right? Okay. I'll do the dimensioning again. So you have to click on the dimension tool, click on the center, and click on the edge here for it to all come out nicely for dimensioning. Then you insert the distance between the center of the circle and the edge, which is 50 millimeters. Okay, so that was that. Then you finish the sketch. Click on the circle again. Because we are trying to create a hole, we then extrude cuts. We are taking it downwards because we want to cut it. We want to like eliminate we just want to make a hole there basically. So ensure that the operation here is to cut, not to join, right? So we click on OK, and as you can see, the model is being created. So if you made it up to this point, please react so I would know if I'm to continue. Is everyone with me? Should I go ahead to the next model, which is this? Okay, okay, I get it. So I would show you how I made the second one. That was for this one. So when as I'm doing this now, I'm making reference to the pictures to ensure that I'm using the proper design. Okay. So similar to what we did, create a sketch because obviously we have to go from 2D to 3D. I choose stop. This is not. Okay. Create a sketch, choose stop. Now begin to use. Now this one is a little bit tricky. So you have to ensure that you follow up as I'm doing it. Or you can just watch and then later you can go back to this. So first I create a rectangle, and as I'm doing it, I'm not even bothered about the sizes or the parts dimensions because I'll go back later to dimension it. So here is 40. While this is interior of the space is 50, 10, 20. While this is 30. Now this is the first part. Next thing is either you use a circle to draw the curved part or you use an arc. For me, I would love to use an arc, a center point arc. So this is the center of this rectangle. You click on it, specify the next point, specify the other point. Oh no, this went the wrong way. So go back again. This is center point. So you have to ensure that you are drawing it the right path for it to follow through. I was drawing it anti-clockwise. So another thing we have to do, we check the 2D model does not have a demarcation in the circular part. Then we also do the dimension for the arc. Already, it's 20 millimeters. Then I would have to trim this for it to look just exactly as it's supposed to. I finished sketch. This is the first part. Then I click on this and extrude. I like it to be in this format. I check the distance, or let's say the thickness. Yes, the thickness. Next thing is to create sketch again for the other features. I use a rectangle. Now, you need to dimension this and ensure that it's in proper dimension. We use 10. I would like to do the circle two as once. Dimension the circle. Circle is 20 millimeters. Now we need to check the distance between the center of the circle and the edge so that you can, this is supposed to be 30. Now this is done properly. Finish sketch. Now I'll keep it in isometric view for me to understand what I'm doing. Click on extrude. 10. I just went to ensure that I could see the sketch. In the browser, all of your actions are being recorded. So this is the first sketch we did before we extruded. These things that look like eyes are used to show and hide your sketches. I'm just giving an emphasis for us to know. Then I'm going to extrude this because I want to make a hole. The operation is to cut, yes. Then let me keep the sketch closed. Think, no, cancel. We'll create another sketch for the upper parts. We can just use a line to demarcate. To do this last part, let me do this here. Then dimension. This point to this point. Okay, 10, correct. We finish sketch and then we extrude. Always keep your models in isometric view if you want to extrude so that you would know what you're doing. Then we go up again by 10. Ensure your operation is to join because you're creating an entirely, like the model you're creating, you're not disassembling anything. Everything has to be compacted together. So join, and that is that. Is there any questions so far? Does anyone have any questions or anything you have to say before we move on to the next thing? Okay. So I would go to the next thing. I was thinking maybe so far so good. I'm coming. Give me a few minutes. Okay. Oh, I think I should have just shared this instead of. Okay, we'll do a quick recap just in case. So far, so good. We've gone through the basics of mechanical design. We've seen what it involves to do computer-aided design. We've seen the features of Fusion 360 and the tools and an overview of the software. And also, we've also gone through the modeling together. So I think by the end of this workshop, we need to we really have a clear understanding of how the mechanical design workflow works, and then you'll be able to get familiar properly with the CAD tools, and then finally design the robot chassis. It's a basic robot chassis design, actually. So we go to design for manufacturing. We'll do a brief run through of that and then go to the design proper. So basically, design for manufacturing is more like a practice of designing products in such a way that it's easy, cost effective, and efficient to manufacture, in the sense that you're able to meet quality and functional requirements. You're able to give that value that you're designing that product or the robot for. So basically, a design can look so good on CAD, whereby you just use your mouse, run around designs, view, zoom it, and then it's looking so nice. But then if it's too expensive or difficult to make, it's actually a failure in the real world, because you're not able to create the balance that the value is supposed to give. You're not able to strike a balance between cost and performance of that design. And this is why we have design for manufacturing, because it ensures that from the beginning, you think about manufacturability alongside functionality. You're able to know that what you're designing should be able to be manufactured. There should be stress analysis, everything should be in check. And then to ensure that once it's manufactured, there's not going to be failure that occurs along the way, whereby maybe some parts are brittle, it breaks along the way, or maybe there are mating parts that are not fitting together and all of that. So we'll look at the key principles of design for manufacturing. So we have material selection. When selecting a material for designing, you need to ensure that the material fits the purpose of that product or the robot you're building. Obviously, when designing, you need to start with checking out or researching for the material to use, because a material that is too expensive, difficult to source out, or even hard to machine can slow down manufacturing. So you need to select materials that are equally functional and easy to process. Sorry. Take for example, the robot car chassis we're talking about. When we are designing it, we need to consider the fact that, okay, we are going to use plastic. Why? Because it can be 3D printed, and then its thickness doesn't have to be too much, because 3D printing takes quite a lot of time to achieve. So another example can be maybe designing a part in titanium for like machine parts can be really, really strong and costly to machine, because it involves a lot of CNC processes when it comes to flashing water, ensuring hot processes are done, and all of that. And then, but it's easier to use aluminium. So there are different design choices that are made when it comes to material selection. Another thing is simplicity in design. Usually, it's always advisable to ensure that your designs are simple and sleek. That's the way I love putting it, because complexity usually adds cost and manufacturing time. And in a manufacturing sector, time is of essence, whereby you need to ensure that there's production in ideal time, there's no time lost due to failure or maintenance lags or anything. So you need to reduce sharp internal corners in your design, minimize unnecessary holes, just go for features that does not require special tooling and increasing cost. And then you need to ensure that your designs are simple, just like I said, because when your designs are simpler, they reduce errors and then minimizes machine cost, because all those complex structures will need a specific kind of machine to design. For example, if you're designing, let me say, a carved wood with different carved structures that will need a CNC. CNCs are really, really expensive to operate and even to own. So when you're designing some kind of things, you need to consider the manufacturability of that design, if it's going to really give a problem or even outweigh the value you're giving in terms of cost. Now, talking about standardization, so it's always possible to use standard parts for your design. Talk about standard bolts, nuts, bearings. There's always standards for engineering design. We have ASME and ISO standards. They are the ones I know. So you need to ensure that you're choosing common screw sizes that can be replaceable, because one thing is to design and that thing is for the maintenance of what products you've designed. So if I design a robot car today and I use bolts and nuts for the mating parts, and they're not able to find those particular bolts and nuts in the market near me, then it's actually a design to failure, because I'll have to go extra mile, paying extra money, and it's going to be costly for me to get those kind of bolts and nuts again. So using standard parts eliminates all this custom fabrication that makes it so generic, and then it speeds up manufacturing and maintenance too when you use standard parts. So talking about tolerance and fits, basically tolerance is just like the allowable difference in the size of a part. Tolerance and fits are basically used for mating parts. Take, for example, a shaft and a hole, or a bolt and a nut. Very perfect example. So basically, when you're designing a bolt, you should ensure that you're able to give a kind of allowance in measurements. Let me say the diameter of the bolt should be given some allowance, and then as well as the nut, for both of them to be able to lock in properly. So all of these little parts come in, little concepts come in when it comes to designing. Also, let me bring it to a simpler way to understand a canned Coke. So when designing a canned Coke, the bottle top and then the main bottle itself, where the cover is being screwed to close it, there's usually a little allowance and tolerance given to ensure that both of them, they are really going to fit in when they are both mated. I'm using engineering terms. Mating means joining two parts together, right? So you need to ensure that when you're designing, your tolerances are not very tight, because when they are tight, they increase machining cost. They should have allowable differences between the two parts, and then they should actually be relaxed enough. So manufacturing processes are basically different processes used in manufacturing a part, right? There are different manufacturing processes. The most common and digital ones we could hear about today is 3D printing, because many people are all about fabrication, designing, seeing what they are designing in real time. 3D printing, we have CNC machining, injection molding. These are all manufacturing processes. And then injection molding is basically used for like large scale plastic parts. So when you're designing for injection molding, you need to like consider what you are doing, the design constraints, because when you're using injection molding, you know that you are going to be doing a lot of mass production, because it's mostly larger companies that have injection molding machines for their large scale production. Then CNC machining too is usually used for precise metal parts. When I talked about a wood carving, also when it comes to metals too, CNC machines are used. So 3D printing, I believe every one of us know about 3D printing. 3D printing is basically used for prototypes and then MVPs. When you're designing for 3D printing, you should also apply the proper design constraints. I need to align your design to the intended process that you want to use, because a part that you design for 3D printing cannot be suitable for injection molding. In some cases, it can be, but then you need to also ensure that the constraints given for this is defined, and then you align it to the process that you decide to manufacture that product with. So talking about assembly considerations, so you need to like consider how the operator or the machine putting the parts you designed using CAD together. Let's say, what will I use as an example? Let's say the Lily robot, the Lily bot. The Lily bot is designed in such a way that it's anyone that has the kit can be able to assemble the parts, use the bolts and nuts given, and all of that. You should ensure that when you're designing, the parts can self-align, right? The Lily bot has like two based chassis whereby you use screws and nuts and all of that to put it together. I don't know if any of us have seen the Lily bot before, but I know Dr. Berry can actually understand what I'm saying. So like, I'm just using that as a case study. So you should ensure that when you're designing, the parts can be able to be aligned, and it's not really so hard for any user that picks it up. This ensures that you save time, you reduce assembly mistakes, and it should not require a very specified or maybe very high experienced person or some kind of measures to be able to assemble together. And also, when you're designing multiple parts that will be assembled, you should also ensure that there are fewer parts, because the fewer the better, reduces assembly time and improves reliability. Now, talking about cost and efficiency, which is a very important part in design process, you need to ask yourself if this part can be manufactured with fewer machine operations, if it uses less materials and gives more optimized value, if it reduces setups, and when you're designing or manufacturing, it chooses efficient processes. The aim of every design or every product or developing is always to minimize cost, because I mean you're giving out value and you're also expecting a revenue in some cases. So you need to ensure that waste is being minimized and cost is reduced significantly when you're designing, to improve efficiency and to even improve the value you are giving. Now, for testing and prototyping, before mass production, basically, you need to create a prototype, either using 3D printing or fabrication, that is machining in workshops. So you need to test your MVPs early enough so that you'll be able to know your design flaws. You'll be able to know that, okay, this joint I used here is bad. I should have used this locking mechanism for this robot part or for this product, or I should have inserted a stop button here. You need to ensure that everything is tested. And in that way, you're going to be saving money. And in the long run, you keep on modifying your product till it's very much efficient. In essence, design for manufacturing as a whole saves money, time, and resources, whereby you're able to improve the overall product quality and satisfy your customer, which is one benefit that I know that design for manufacturing gives. So we talk about design trade-offs and constraints in robotics, where we see issues on weight and strength analysis, or let's say comparisons. Yeah, better still. Talk about comparisons on cost and performance. So in real life, robot design is about choosing between options. Because when designing robots, everything can be perfect. We need to make certain choices because you're designing, you're making research, you're giving improvements here and there. You're actually working towards a goal, which is to give a value that you have in mind. So when it comes to weight and strength, you need to know that, okay, there are certain things to be considered because, okay, let's say if we make a robot very strong with heavy materials, it can likely not move because it's heavy. I mean, so in essence, we see where material selection is playing a role here. Also, if we make it light, it may not also be strong enough. So we need to ensure that weight is balanced. There's a balance between weight and strength to ensure that there's a balance across the robot and whatever the robot is doing for you, whatever value it's giving. I would always like to use the word value because in essence, you're solving a problem, you're creating value. So we must always ensure balance because it's just very important. Now, considering cost and performance, yes, when we're making robots, we will say, oh, this robot is to detect diseases in a farmland or to do this and to do that. We will now be imagining, okay, I need to use these sensors, I need to use these actuators. They are going to make this robot very, very nice. But now you're not thinking about something. You're not thinking about the costs. You're not thinking about how much output and how much efficiency those sensors are going to give you. So you need to create a striking balance between both. Sometimes when you even pick cheaper options and cheaper parts, they still get the job done. And also sometimes the best performing robots too can need very expensive parts and sensors and actuators and all of that. But then you know that you need to actually weigh your options and then know what you really want, know the value you're trying to create, and then building. Because sometimes when you even reduce the cost and try to use anything, you can see you also lose performance. Because definitely you cannot just say you need results of a LiDAR mapping, a robot that includes LiDAR mapping, and then you want to use an ultrasonic sensor. It does not work that way. So you need to weigh your options properly when you're making decisions in design. Other examples can even be speed versus accuracy, because sometimes if the robot moves too fast, it can lose precision. So you need to ensure proper calibration is done. Then talking about battery life and power, these are other examples I'm just giving. Sometimes we may say stronger motors require more energy, but then you need the stronger motors for your robots. But then you now have to consider the battery life, the type of battery, and power management constraints. So the main thing here is in robot design, you need to ensure that your trade-offs are smart. Your decisions are always tailored depending on the goal, your budget, and the environment. Very, very, very important. So we'll go to the 3D design and modeling of a four-wheel drive robot.
Chidinma,
For
before you
this,
start that, you have a question in the chat. Aji
okay.
Safe has put in an image and he wants to know, how can you make a coil-like structure like that in Fusion 360?
Okay, let me check it out because I'm trying to open the image. I don't think so. I can't seem to. I can't see the image on.
Let me see if I can send it to you in a message.
Okay. I can't seem to see it either. Okay, I just saw it now. Okay, for this, you need to actually, first of all, you need to determine the views and what the, this looks like a spring, right? There are tools on Fusion 360 where you can use to achieve this. So first off, you can design the shaft, first of all. After designing the shaft, you then design the grain base. I hope everyone can see my screen. Okay, yes. You then design the green base, right? From there, you can now add on, just the way I was creating sketch, I click on the last part I designed because I'm more like joining everything all together. Then this is more like a torus. If you go to Fusion 360, you would see a figure like that, a coil, something like this. So you really want to actually, determine the distance or the length. Are you guys seeing what I'm doing? Did I answer your question? I can't seem to get a response. Okay, let me go back to the picture. So first off, you need to design this part, right? Then from there, you can then add the lemon green part, right? Or is this steel? I think it's steel color. So you need to do it step by step before you finally add this spiral coil at the edge. And then you're going to do it in such a way that, oh God. You're going to do it in such a way that you follow it up one after the other. Do you get me? Okay. So just start, if you start with the, if you navigate through the Fusion 360 tools, you will see rod or a pipe. You start with that, then create sketch on it. This you draft out for the conic, because I'm just believing this is a conical shape structure. Then you then add this plate, this green plate on it to create a sketch. Then you attach the coil to this plate, and that is it. Okay. Does anyone have any other questions? Can I go ahead? Please, I don't know if you guys can hear me.
So
Let
I
me
say
check.
go ahead and get the card done so we can wrap up in about 15 minutes. And then I just, Safe, maybe stay back with Chidinma at the end to talk about your coil project a little.
Okay. So for this four-wheel drive robot, we are going to use a single base because of time. That's why I did it this way. And then we would design wheel mounts and the base. For the electronic components, they are all in the drive link I sent. So you can actually download them and then upload them in your Fusion 360 workspace. I will show you how to upload them before we start. I think we can go over to that now. Okay. So we can create a new design. So I will show you how to upload your documents. At the beginning of the class, I created this project. So I would go through them. Now for this Robot Car Chasis, I will click on upload, click on select files. By then, I've already downloaded some of them. So I just highlight everything, click open, then upload. Then your electronic components that are already modeled, they get into your workspace. Okay, I think they are all done loading. Yeah. So the next thing we have to do is, since we've gotten the components, we create sketch for the chassis. I like using top. So I use more like as a center triangle. Then before I did the design, I had to do some measurements. I checked the length and the thickness of the length, first of all, to determine the length. I checked the length of the DC motors and I figured out they were like about 65 millimeters, right? So because we are going to design a four-wheel drive, means that each length would have two DC motors, which is 65 plus 65. That's about 130. So I decided to make here 150 because there has to be space in the middle. So when dimensioning and checking out for measurement, you need to also know what and what you're adding. So same thing goes for the other side. I think for this side I made it 120. Because sorry, I'm actually checking my measurements on my book. Okay, yeah. So here is 150, here is 95. So you finish sketch. I don't want to make any fillets around. So I just have to extrude. Now, like I said initially, you need to check you're designing for manufacturability, right? So definitely the thickness of this design, I'm I'm looking to design for 3D printing. So the thickness of this design shouldn't have to be much because I mean 3D printing is for prototyping. So I used 5. Yeah. So at this point, we then create our mounting holes for the DC motors. Create sketch, and then now this is where one of the DC motors will be. So for my measurements, I had like 22 and 18, but I'm giving tolerances. So for this to be 25, how this will be 21. So from there, it's okay, 21. So if you check your DC motor, you would see that there is usually a square part at the end. So you need to create a space for that. I want to use a center point rectangle. So this was 3. Okay, I think this was 5. And this was 3. So now you use your dimensions to ensure that they are of equal part. Half of 25 is 12.5. Yes, to make sure that it's at the center. So the next thing we have to do is to finish sketch and then extrude. I prefer putting this in. Now, our DC motor was 65, so a part of it has to be out for you to know that there's a DC motor there. So now in this measurement, you're seeing minus, right? So basically, there's a way distance is being applied to when you're designing. When you're moving left, it can indicate minus, and then when you're moving right, it's positive. So just for you to know that all of this applies, then you can see this. So from here, we make a sketch to here. Now, mm, mm, I'm redoing the extrude. I made a mistake. This is supposed to be a new body and not joint, because this is more like a different component that will be assembled to the robot chassis. I hope you get what I'm saying. So within this, it was minus 45. I'll just quickly do this here. So now, this can be a bit tricky. You just have to follow me up squarely. So we're trying to create a slot whereby this motor can be inserted here. This space is too small. So I'll create a square. Let me see. I'll use the slot symbol instead. I'll use the center to center slots. So I'll choose this place and here. Now, also, if you check a DC motor, you will see that there are places where a screw is supposed to be pointed out. So I'm trying to create tiny circles. I'll still dimension this. So I'll use my dimensioning tool to ensure that this is done in the right way. This is supposed to be 2, about this is 3, 2. I'm giving it 3 because 3 is the diameter of the bolts that are going to be going through it, while the radius of this is 5. Same thing goes for this. Yeah. Let me check the distance between here and here. Okay, it's already symmetric. So I don't think there needs to be any distance created again. So now I'll finish sketch. Right. This is symmetric. Yeah. So the next thing is to extrude. So once I click extrude, I need to select the profile that needed to be extruded. So I just select this, and this. You need, no, you need to ensure your design is being carried. So I'm extruding to cut out because I'm trying to create a slot. So when you're extruding to cut, you don't need to check the dimensions. And of course, the operation should be to cut. Then that is that. So I can't seem to find. Okay, yeah. So from here on, I'll finish up the slot. We create another sketch. So from here, you draw a rectangle. So at this point, we are trying to like fully position the slot so that it can fit into the DC motor while considering tolerance into. So we check distance between here and here is 2.5. Now distance between here, enter, here and here should be the same thing, 2.5. Now we need to check the distance between here. The length of the length of the side of this for the DC motor was about 18.5, but I'll leave it as 19 because we need to ensure that there's proper tolerance then that needs to be done. Same thing goes for here. Okay, here is proper 20. So the next thing we need to do is to finish our sketch and then keep it at home so that we'll have a proper 3D view. Then extrude. We go at a distance of 40. Okay, now we finally created a slot for the DC motor. Now we'll go ahead to create mirrors of this slot all around. So all I have to do now is to go to mirror. Yes, yes. So we need to select the object that we're mirroring, then click on select plane. So as you can see, once you click on select plane, automatically another one has appeared under. So this is how seamless it is to design on Fusion. I will also go to mirror again. I'll select the object. Select the second one. Then I'll the plane you select determines where it's going to be at. So now these are how these tools are really functional in our design. So next up, I think we are out of time, so I will really rush up. Next is to start bringing in our component. So I'll check the data panel. I'll bring in the motors first off. Now, when you bring this in, network is lagging. Okay, yeah. So that's but when you bring this in, it can really be quite tricky because you need to move it around. From what you know about motors, you would know that this is for this part. So now you need to actually link it system around to, oh my god. Mm, mhm. I'll click on this again. Sometimes these things can get weird. You have to drag it to drop. So now we can see that this hole is supposed to be mounted to this. So all we need to do is to go to assemble, click on join, then we select this. Please watch carefully. Ensure it's in the right hole. Then only the motor goes in. Select OK. The same thing we're going to do for the tire. Click on join. Now select this part, orbit it around. Then you know that the tire is supposed to be attached to this place, so you click on it and the tire is being joined. Select OK, and that is it. So we're basically going to do a mirror. We'll use pattern instead. We create object. Make sure to select component as your object type. Now to select axis, I want to make sure that I'm doing this right. Sorry, I'm supposed to select axis. I think there's an error. No, yeah. Okay, I think I got it figured out. This is the final thing. Okay. Yeah, confidence. So just select this. I clicked on mirror. I made an error by clicking on pattern. So select mirror plane. This part can be a bit tricky. Then the tire goes to the other part. Click on OK. Same thing. Select mirror plane. The plane I'm selecting depends on where I want my tires to be. I just want to make sure that this can be viewed. Then select. Okay. So, oh, there's an error. You see that the motors did not join in the last part because I did select the motors as well. So I'll just go back and do what I did initially. I'm almost done. So mirror, I've highlighted it too, the motors and then the tires too. Select mirror plane, this, and everything is attached. Okay. So the next now be to mount our electronics components. So I quickly go to the data panel. We'll basically be using, we would need a battery holder. Now, this is where you need to ensure that you're able to position it properly. This should be 0. So just ensure that it's properly mounted. I would have loved to add up mounting holes and everything, but I think next thing, add your Arduino. So for the main thing now, we're already done, including the motors, joining them. The more advanced ones will have to be to use Mastercam to add in screws and nuts. Okay, so I'll have to add this. Oh, I made a mistake. Let me add the Arduino again. So I'll just add the Arduino and the motor driver. And I think that will be that. So where designs like this is actually useful is probably you want to design a Vision 360 and integrate it for like a design overview, or maybe even integrate with ROS. It just depends on you. So this is more like an overview of how to go about designing. I made the same mistake again. I was supposed to just click OK here. So yeah, I think we'll just have to call it off here. A quick one for the appearance and the materials. You can just type you can just click A on your keyboard and you would see a section whereby your appearances and choice of materials will be selected. These are the materials. So for this, we're using plastic. Now we can see ABS, you can see, let me check if I can see other 3D printing materials. This is also used for 3D printing. So I will just have to choose any one of my choice. Ensure it's on the body of the component. I'm dragging and dropping actually. Let me close this so that. Now there's also a part where you can change the color. I will show that. To change the color, you just have to right click and click on edit. So depending on whatever you want, it can be any color for you. Hope you can see it here. I think I'm seeing questions in the chat. Okay. So I think we're going to stop here for now. This is basically all about designing a simple robot car chassis. So I would like to know if you have any other questions or anything. Oh, one more thing. I'm trying to highlight all the parts, but if you can just select everything here, this is why you have the browser. Hope I'm not missing out on anything. So I just click on joints and everything is joined together. Let me check. Yeah, so that is all. So if you have any questions, you can please ask now.